All right, guys. So we are back to the next lesson on 20.2 is the unit. So this is dealing with electric force with multiple charges at the same time, electric field, and then electric fields with multiple charges. So it's the superposition, adding multiple things together again. So last lesson we talked about Coulomb's law, which is described in this equation. So F or Fe for the electrical force is equal to K, which is the Coulomb's constant, which we use 9 times 10 to the 9th for, times the absolute value of Q1 and Q2, which are the two charges that are involved, and then R is the separation between those charges. So again, if we had a charge here, which we could call Q1, and a second charge, Q2, and they're separated by some amount of space, which they call R, we can find the force of either attraction or repulsion based on that formula. So again, we also need to just remember that, if you have like charges, so if we had two positives, there'd be a force repelling them. So the force from 1 on 2 would go to the right because they're going to try to push away, and then the same force in magnitude would go the opposite direction of 2 on 1 going to the left. So this force pushing to the left and this force pushing to the right are the same amount of force. If we had negatives and negatives, it would be the same thing. If we had one positive and one negative, though, those forces would become attractive. So we're going to use this equation several times, essentially. And for superposition, you have more than two charges. So if we just have two charges, this is what that equation discusses, the force between two charges. But if you have more than two charges, if you had a setup with like 3 charges, then you're going to have to do vector math and a little bit of trig to help you out with that. So we're going to work through a problem just to kind of express it at first. So it says, find the net force acting on QA. So QA, this one that I just circled, is the charge that we want to know what the net force is acting on. So we're going to basically say like QC and QB are fixed, and we want to know how they would influence QA. Which way would they push on QA? So just listing out what these things are. So QA is 5 times 10 to the negative 6 coulombs or microcoulombs, and it's positive. So that's a positive charge. B is also positive, and then C is negative. We don't worry about the interaction between B and C. We just worry about the interaction between like B on A and then C on A. So if we were drawing in those forces, so I'm going to use a different color, B and A are both positives and they would repel. So B would push A away from it. So that would be the force of B on A. So that's going to push it to the left or in the negative X direction. Reverse to that, A and B, A is positive and C is negative, so they would attract, so there'd be a force pulling upward on A from C, so the force of C on A. And we're going to need to calculate each one of these forces using Coulomb's law. The space between those charges is given in the diagram. So overall, there's going to be a force trying to B tries to push A to the left, and C tries to pull up on A. So the net force would be kind of the combination of those two. So we're going to use a little bit of vector math. So if this is the force from C on A, and this is the force from B on A, then the net force is going to go up and to the left. So we're looking for F net, the resultant force, and our angle theta. So the force includes not only the amount or the number, but it also includes the direction. So if you need some vector review of like how to approach a situation like that, it's just right triangle trig. I've on the handout included a link to a flipping physics video where they talk through it, and it's not bad. It doesn't use forces, it uses displacements, but it's the same type of math, so it should be a good review. So I've got the work done up here, so I'm just going to delete this. So again, we're using Coulomb's law. The force is equal to K Q1 Q2 over R squared. I used notation E, so that's like times 10 to this. So this is 9 times 10 to the 9th, which is K. 5 times 10 to the negative 6, because micro stands for times 10 to the negative 6. B is 6 times 10 to the negative 6, so that's that one. And then I take that numerator and divide it by 0.25 squared. So I used 0.25 because that's the separation between A and B, and make sure you square it. If you put that in your calculator correctly, you should get something like 4.32 newtons, and it should go to the left. So we've determined left from the picture. Nothing in the equation tells me it's going to the left. For the next one, for C on A, how C affects A, similar kind of work, K, QA, QC divided by the space between C and A. So 9 times 10 to the 9th, 5 times 10 to the negative 6th. This one's a negative 3 times 10 to the negative 6th. If you want to include that, you can, but it's absolute value, so it doesn't really make a difference. And then I'm dividing it by 0.135 squared. The part where people forget is the squared here on the R, so make sure you're doing that. When I did that in my calculator, I got approximately 7.4 newtons going up. So we have the two sides of the triangle. This side is 4.32 and this side is 7.4. So we're going to just do the vector math and get to the answer. So I just shorthanded it and did the Pythagorean theorem. So basically a squared plus b squared equals c squared. So the x direction squared plus the y direction squared equals the hypotenuse. So I got 8.6 newtons when I combined those two components, so the x component and the y component. And then for the angle, I used the inverse tan of the y component over the x component. So that's the math I put on my calculator. Make sure you're in agreement mode. So this is about 60 degrees, and it's going above the negative x. So that's how you would apply that kind of idea. So hopefully that's not too bad. It's just using multiple charges to find the net force on one particular charge. And you could have these in straight lines, but this one is a little bit better example because it makes you do the vector math in multiple dimensions and use the Pythagorean theorem and the inverse tan to do the trig. So the next concept we're going to get into is electric field. And electric field is similar to electric force, but it's not exactly the same. So before we get into electric field, you probably, when you took your first general level physics class, talked about different types of forces. So we classified them into groups, and the two groups were contact forces and field forces. So contact forces were forces where things were touching. So if I pushed or pulled on something with my hands, that would be a contact force. Field forces are ones where touching was not required. So like the force of gravity is a field force. Magnets are a field force. Electric force is a field force. So the charges don't actually have to touch to influence each other. So the force that an electric charge exerts on another is a field force, and if it is a field force, that means there has to be a field creating the force. So the electric charges create fields around them, and when another field or another charge enters into that electric field, a repulsive or attractive force occurs. So it's very similar to like if you were talking about the Earth and gravity. So if we drew a picture of the Earth, so I'm just going to draw a circle. So if we say that's the Earth, right? And let's say we had an object and we were going to drop it. So this is the object. The force of gravity would pull wherever that object was towards the Earth. So it would pull these masses inward towards the Earth. So that Earth is creating a field, and if you got close enough to the Earth, then that field would pull you in. So if in space, there's these asteroids going by or satellites, and if it gets close enough, then gravity is going to pull it downward and cause it to run into the Earth. So that's why we have meteor showers and things like that. So the key difference here is we're not talking about the force, we're talking about the field. So we're talking about the area and sort of the effect that it has if anything comes into that area. So around this Earth, or any massive object, there is this field where it pulls in things. So if you put mass in this object, it's going to pull inward, but that field is there regardless if there's a mass there or not. So that's what we're talking about, is like the field. Similarly for charges, like you'll have a charge, whether it's positive or negative, it doesn't really make a difference. Their directions are different. That's the one thing that's kind of different with electricity. But around that area, there is this influence. So like it affects the space around it. And if you put another charge in it, then it would experience an electric force. So if this is positive and this is positive, that would repel it. If you put a negative charge over here, it would attract it. And then same idea for the negative. We have this field around it, and if we put a positive charge close enough to it, it would attract. If we put a negative charge close enough to it, it would repel. So the field is there regardless if those charges are there or not. So it influences the space around them, and if you put a charge in there, it would have an effect. That's the concept that an electric field has. So the definition of an electric field is it's the field that surrounds a charged object in which another charged object would experience a force. The symbol for it is a capital letter E, and it is a vector. So vector fields have directions just like vectors do, like we did electric force. The direction follows the electric force would act upon a positive charge. That is really important. We always draw our electric fields and visualize our electric fields based on how the field would influence a positive charge. Okay, if it's a negative charge, it would behave the exact opposite way to the way that your direction you've drawn would go. Okay, so if we have a positive charge and we put a positive next to it, so our test charge, which is this charge that it's acting on, it would repel it away. If we had a negative charge and we put a positive close to it, it would pull it in and attract it. So the field direction is based on how it would influence a positive charge. Okay. So in general, the equation to calculate electric field strength of an electric field acting on a charge. So this is important. You can calculate the electric field that is acting on a charge, or you can calculate the electric field created by a charge. But this one is for acting on a charge. That's this equation. So the electric field is Fe divided by Q. Q naught is the test charge, or whatever the charge is in the field. And then Fe is the electric force. So if you know the electric force, so let's say we had a charge, which we'll call Q, and there's an electric force acting on it, and we knew this number, and we knew how much charge there was. If we just divide those two numbers, we'll get the electric field. So electric field is E. Fe again is the electric force, and then Qo is the charge. The unit for electric field is newtons per coulomb. So force is measured in newtons, and coulombs is the unit that we measure charge with. The other equation that we use to determine electric field is like the electric field created by a charge. So this one is saying, okay, we have a charge, and I'll just make it a positive charge here. So we got some Q, and we want to know how strong the field is at some point a distance of r away. So if we say this is the point where we want to measure the electric field, what is the strength of the electric field at that point? This is the equation for it. If you notice, this is very similar to Coulomb's law, but there's only one charge. So we don't have that second charge to influence. We're just looking at how is the space influenced by this other charge. So E is equal to KQ over R squared. Same ideas that are in Coulomb's law. So to calculate the magnitude of an electric field at a point in space due to many charges, you got to use superposition. So it's basically the same idea we just did in the beginning of this video, where you drew vectors and you determined kind of the amount of each vector at a particular point, and then you have to do vector math or trig to figure it out. So very, very similar to superposition of electric force. So I'm not going to go through an example with that because it's basically just using this equation for multiple charges in space. So if this is the point, from this positive, it would influence it going that way. So that's the electric field. We'll say from, if we call this one 1. If I had a second charge, so if I put a charge down here and let's say that one's negative, it would try to pull that positive charge inward towards it. So that would be maybe 2. So that's E2. And then you would do vector math to figure out, oh, okay, these two are adding together. So, whoops, I wanted to change color. It's pulling kind of down and to the right in this case. So that configuration of these two charges at this position, how would it influence it? It would pull it kind of down to the right. So this would be the net or total electric field. And you could do the same kind of trig where you make a triangle and you figure out theta and you're solving for the hypotenuse. So again, not that different from the first example we did in today's lesson. All right, so some other ideas about electric fields. We draw what are called electric field lines to visualize electric fields. And the electric field lines represent the magnitude and the direction of the electric field. They don't really exist. There aren't these imaginary invisible lines out in the middle of space. They're just there to help us model and kind of visualize what's going on. All right, so some rules for drawing electric field lines. The first rule, lines leave positive charges and enter negative ones. So again, it's how it would affect a positive. So if I put a positive anywhere along this kind of these positions, you would see it's going to get pushed along those electric field lines. If I put a positive charge next to the negative, it would pull it in. So again, you can kind of see and visualize how that works. So lines leave positives and enter negative ones. The number of lines in an electric field diagram is proportional to the amount of charge. So the more charge you have, so if you increase the charge, you increase the electric field. And that just goes along with the proportionality of the equation. So again, E equals KQ over R squared. So as R gets bigger, or I'm sorry, as Q gets bigger, E is going to get bigger. So that has to be shown. So if you had two different charges and one was, say, 3 times bigger than the other one, then it should have 3 times the number of lines. That's how it works. So that's what that note's saying. Electric field lines can't cross or touch, but they can kind of curve or bend, so the word line is a little misleading. And then the closer the field lines are together, the stronger the field. So as you're closer to the source of the electric field, the lines are closer apart. As you move further away, they spread out. So when you're close to it, R is small. So as R decreases, E is going to get bigger, and that's the inverse, or they're inversely proportional concepts. So if you get further away, if R gets bigger, like as we move further and further away, the electric field lines spread out and radiate away from each other, so the electric field gets smaller. So that's another kind of way that we show that in these drawings. Another thing that I just want to mention is in reality, field lines go in all dimensions. So this is 2-dimensional. It's going X and Y, but it also comes out of the board, but I can't diagram that very well. And again, as we move apart or spread out, the field lines spread apart and the strength decreases. Sometimes you'll have pictures, and in very special cases, which you're going to learn in the next unit, we'll have what are called capacitors. So a capacitor is basically 2 charged metal plates. One has a positive charge, one plate has a negative charge, and we would produce what's called a uniform electric field, where the lines are all pointing in the same direction, and they're all pointing in the same direction, and they're all equally spaced. So that's what's called a uniform electric field. So the electric field between those 2 charged metal plates would be going from left to right in this diagram. So that's what's called a uniform electric field. But if you just have a charge of some sort out in the middle of a space, they look more like this. So let's practice and try to see if you guys can come up with some drawings. So it says draw the field, or the electric field, produced by 2 equal positive charges that are next to each other. So you would draw one positive charge and another negative charge, or positive charge, and you'd see how they'd interact. Remember, the lines can't cross or touch, so those lines are going to have to bend. So this is what would happen for a 2 positive charges. So again, the lines are moving outward. They would go towards each other, but they would repel, and the lines would curve and bend. If you had 2 negatives, it would look very, very similar. It's just what would be different. You should have hopefully gotten that the charges would be coming inward. So because the negative charge has an inward field, lines go towards negatives. And if we had one positive and one negative together, it would look something like that, where the positive field lines go towards the negative, and they would just, make that path and go along there. So again, if we put a positive charge on any of these spots, so let me change color. So if I put a small positive charge here, it would follow that path and go around and get to the negative charge. If we had a positive here, it would, follow this path and go that way. So if we put a positive in the middle, exactly in the middle, where you see no field lines, that's where there is no electric field. So if I put a positive here, it's equally spaced. It should make sense that, like, oh, those forces are going to be balanced. So there's like a force going to the right, a force going to the left, and they would be equal. So that's why the charge would just sit there. So there's no net force and no electric field there. The other thing, again, just I want to mention, if you had a negative, it's going to do the exact opposite. So if I put a negative charge here on this, it would pull it inward towards the charge. Or if I had a negative here, it would repel it the other way. So just to be careful, we, again, draw our field lines based on positive charges. All right, so we're going to end with some conceptual questions. So instead of doing the math with those two equations, we're just going to kind of look at them conceptually. Again, this is like, it says rank in order from the largest to smallest the magnitudes of the electric field at the black dot. So the black dot is where we're going to measure the electric field. There is no charge there. We're just measuring the electric field. So each of these charges here in situation 1, 2, 3, and 4 are creating an electric field. So that's going to be the KQ over R squared equation. So K is a constant, so that's going to be the same for all of them, so that's not going to have any impact. And we want to get the electric field to be the biggest. So the electric field is biggest when Q is big and R is small. So that's when you're going to get the big electric field, because E is directly, or Q is directly proportional to E, and R is indirectly proportional to E. It's going to be small, so you're going to get a small electric field when the opposite takes place. So if you have a charge that is tiny, and you have a separation that is big. It's R squared, so the separation actually has a bigger impact than the amount of charge. But if we look at it, we have Q, 2Q, 2Q, and Q. So if we're just ranking based on charge, it would be these two would be first, and then these two would be last. And then the bigger the electric field strength, the smaller the distance. So 3 has the best combination of lots of charge and a small distance. So I would put that first in my order. Then we would do the one that's smallest. The one that's smallest is going to be 4 because it has the least amount of charge and it's the furthest away. So the other two is the ones that we have to consider a little bit. So if I plug in the numbers for this one, it would be K Q over R squared. And for this one, it would be K 2Q over 2R squared. So if I simplify this out, just moving over a little bit, it's going to be K 2Q over 4 R squared. So if we group the numbers, 2 and 4 gets you a half. So this one is actually bigger. 1 is bigger than 2. So this last one here is the correct order. If you wanted to prove that, say this one is the biggest, it would be K times 2Q over R squared. So that would just be 2KQ over R squared. So this one is twice as big as that one. This one is twice as big as 2. And then for the last one, it would be KQ over 2R squared. So that would get you KQ over 4R squared. So this is a quarter, this is a half, so, and this is 2, 1, half, and a quarter. So that's the right order. So that's like the strength of the electric field at a certain position based on that equation. All right. The next one is looking at directions and how it would influence. So again, same idea, but now we're going to have to use multiple charges. So and figure out the electric field strength. So it says all charges have equal magnitudes, so the magnitude doesn't really make a difference, and the constant's not going to be a difference. So it's really based on R squared. So that's the idea. So it says for case 1 through 4, is the electric field at the dot directed to the right, directed to the left, or is it like canceled out and 0? So let's imagine what's going to happen with these electric fields. So if we put like a tiny plus, that's the way it would influence it. So each one of these has multiple charges, so you just have to look at one charge at a time. So if we make the positive charges, I'll highlight them all in one color. Let's make the positive charges green. So these are all positives that I'm making in green, and they're going to create electric fields at the dot, or at this positive. So this positive and this positive, they would repel. So that's going to be one electric field going that way. This one is closer and it's the same amount of charge, so it'd be a bigger electric field going to the right. Oh, this is positive too. Both of these are going to the left, so they're going to add together to produce those charges in those fields. Then the negatives, which I'll put in a different color, we'll make them blue. Those negative charges are going to try to attract the positive, test charge towards it. So this negative charge is closer than the positive, so it's going to have a bigger field. So it's going to have a bigger arrow going that way. This one is smaller, so it's going to be going like that. No negatives here, and then this negative would pull to the left, and this one would pull to the right, and they are equal because they are equally spaced. So let's try to get the overall effect. So if I add those two vectors together, for 1, it would definitely go to the left. So that's going to be to the left for 1. So that's right. For 2, we have these two added together. So it's a bigger electric field going to the right. So that one's going to be right. For 3, both of these are pushing to the left. So they would definitely be left. And we said these are equal, so they're going to cancel out. So that's going to be 0. So B, this column, is the correct column to decide the directions of the electric fields based on these configurations at those positions that were marked with the black dots. All right, the last one here, it says what is the electric direction of the electric field at the dot? So this is our dot. And we have to kind of figure out which of these A, B, C, or D is going to show me the direction of the electric field, the net electric field. So, so for the first one, again, we imagine this is a positive charge at the dot, and this red charge is going to push this away. So it goes linear away, so it should kind of go up and to the right. So that's going to be, if this is 1, I'll just call this electric field 1. Electric field 2 is in blue, so let me change color. So this negative is going to try to pull it towards it. So that's that. These look to be equally spaced away from horizontally and vertically from the distance. So I would say they are equally distance apart. So E1 and E2 are the same amount of field. So if this is going up and to the right and this is going down and to the right, the net is just going to go to the right because they're going to kind of cancel out. This one's pushing up with the same amount of force that our electric field that this one's pulling down. So the net is just going to go in direction C, which is the correct one. Okay, so that's it for electric force, electric field, and superposition of those ideas. So hopefully that made sense, and you can practice and ask some questions and answer questions if you need. So have a good one. I'll talk to you guys later.